This video will introduce proton chemical shifts by showing a chart that is fairly common for hydrogens attached to various functional groups. However, it's more useful if we break this down more systematically. Electronegativity of attached or nearby elements has a significant effect on chemical shifts. The left column is a series of compounds with the chemical shifts of the methyl groups attached to elements ranging in electronegativity from carbon to the more positively charged nucleus of nitrogen onto oxygen and then with fluorine. And you can see that there's a steady progression in the deshielding effect as a positively charged nucleus draws electrons toward it. With third row elements, such as tetramethylsilane, the nucleus is relatively electropositive, so there's more electron density on the methyl groups. But as the nucleus becomes more positive with phosphorus and sulfur and with chlorine, electron density is drawn from the methyl groups to the third row nucleus. For the halogens, for chlorine, bromine, and iodine, the shielding effect increases as you go down the periodic table, as additional electron shells shield the positively charged nucleus. The effects on chemical shift are somewhat additive, so that diiodomethane and triiodomethane are increasingly more deshielded. And you're probably already familiar with this from examining dichloromethane and trichloromethane, or chloroform. Formal charge can also affect chemical shift. So if trimethylamine has a chemical shift of 2.12, the protonated trimethylammonium compound has a chemical shift that is now somewhat deshielded. This also occurs with Lewis acids coordinated to the nitrogen. That increases chemical shift even more. And for the amine oxide, which now puts a formal positive charge on nitrogen, we see also a chemical shift consistent with deshielding. The other factor that significantly affects proton chemical shifts is diamagnetic anisotropy, which is associated with pi bonds on the effect of the interaction with the magnetic field. The pi bond of an alkene causes the protons to be relatively deshielded, as we see with chemical shift in the range of 5 to 6. For an aldehyde hydrogen, the combination of the pi bond and the electronegative oxygen now greatly deshields the hydrogen of the aldehyde, close to 10 parts per million, but the methyl group is also slightly deshielded by proximity to the carbonyl pi bond. This effect also occurs with benzene, related to the ring current of the aromatic ring. Whereas for an alkyne, electron density is in a cylinder around the carbon-carbon bonds, so that the hydrogen is only slightly affected by the deshielding effect of the electron cloud. The effect of anisotropy is exemplified in the proton NMR spectrum of a simple alkene, trans-2-hexene. The hydrogens directly bonded to the alkene carbons, even though they are not chemically equivalent, these peaks very nearly overlap. The anisotropy effect falls off with distance, so that the allylic methylene and allylic methyl groups are slightly deshielded relative to the other methylene and methyl groups for the remainder of the alkyl chain. Resonance delocalization modifies the effect of diamagnetic anisotropy consistent with partial positive or partial negative charge corresponding to minor charge-separated resonance forms, as we can see for 3-pentene-2-one. The carbonyl group conjugated to the alkene deshields both of the alkene hydrogens, but the alkene hydrogen that is attached to the carbon with partial positive charge buildup is more deshielded than the other alkene hydrogen. For the vinylic ether, a minor resonance form with electron donation from a non-bonded electron pair on oxygen creates more shielding at the hydrogens that are distal to the position of oxygen bonding to the alkene. This effect is also evident for aromatic rings that are substituted with electron withdrawing groups, such as metadinitrobenzene. With a minor resonance form, putting negative charge onto the nitro group oxygens form a positive charge on the carbon that is ortho to both nitrogens. We also see resonance effects for the other ortho hydrogens, and even for the hydrogen that is meta to both nitro groups. The inductive electron withdrawing effect deshields the meta hydrogen relative to the proton chemical shift of benzene.